I'm the only operations research analyst at the company working with an energy team, and we're looking to assess risk of vulnerabilities on energy and utility systems. And I'm currently using the tool @Risk, which is here at Inform, so we got to network a little bit, but it's new and it's an industry standard way to assess the risk of letting something go unremedied. We involve probability and statistics. We're looking at probability of occurrences and frequency, looking at an impact that something as simple as an ice storm could have on your electricity, and then we're going to put that into a simulation model and simulate that this event could happen 1,000 times and output results that the simulation tool gives you an advanced look at something that you can't collect data over time for.
One of the more fun things that I do is NCAA tournament predictive models. So there we use some Bayesian probability, some Markov chain models, some logistic regression, and have a pretty good predictive model of which teams will do well in the NCAA tournament, which teams will go further. And so I guess 3 years ago now, we predicted the whole last 3 rounds correctly before the tournament even started. Last year there was a website that tracks 50 or so different predictions, and our method beat the other 50 by at least 3 games. So that's a fun project.
Supply chain optimization basically involves trying to understand how to make the best decisions in order to acquire the materials that you need in order to manufacture products or to assemble different products. So, for example, if you are building a laptop computer, clearly there are a lot of different types of components that go into that, and companies such as HP and Dell, etc., have to make decisions about how many of each different type of component to purchase. When should they purchase them? In what quantities should they purchase them in order to take advantage of different sorts of economies of scale? So supply chain optimization involves basically trying to figure out what to buy, when to buy it, and at what price.
But on the other hand, I've been working on a problem which are a set of issues which we like to call computational sustainability. So I've been working on trying to save a species of woodpecker. That if this is the red cockaded woodpecker, it's on the endangered species list. And so we're trying to understand how we can guide, again, to give quantitative models for thinking about how to allocate funds so as that the Conservation Fund, which buys tracts of lands for the preservations of species. So this is, entirely different range things. The same sorts of issues come into play. You've got degrees of stochasticity, their randomness, and how the birds populate, how things affect them. But you've got limited resources, the money in which to spend, in which to make the system as efficient as possible. So in particular for the woodpecker project, it really boils down to a very large scale, first initially stochastic integer program, but in fact we're solving with then simulating it through a deterministic integer program. The range of land means that we're solving a network design problem on millions of nodes. And 20 years ago this wouldn't have been thought, and it's not just the advances in computers, of course that's an important role in terms of the availability of large-scale memory and the like, but it's really the advances in methods to attack these problems that has really been the driving force of why we can actually get reasonable solutions.
So I've worked on a number of different projects over the course of my career, both in academia and outside of academia. One that particularly comes to mind was a project that I worked on several years back while I was working for a company as a supply chain optimization consultant. And we worked for a plastics manufacturer, so a manufacturer of injection molded plastics, all the kinds of things that you can go out and buy it, choose your favorite big box store, and you need to move and you go out and you buy a lot of plastic tubs with tops or different laundry baskets and things like this. So this is basically a company that had a very interesting manufacturing environment. Lots of different types of molds that were in place. These are basically, you can think of them as the shells that hot plastic gets squirted into, and then several seconds later mold opens up and out pops a purple laundry basket or a purple tub or something like this. So one project we were involved in was to helping this particular company schedule their manufacturing operations. And it was very interesting because it involved a lot of different sorts of discrete optimization problems. You wanted to figure out not only, given you have a certain number of machines, what sorts of tooling you wanted on those machines, think of it as what sorts of shells you wanted to put on there, but also there then came the question of, okay, so if I have the tool that is a laundry basket, okay, now I'm going to make a lot of different colors of laundry baskets, and what order am I going to make those? Clearly it wouldn't make sense to make white laundry baskets and then immediately switch over to black or very dark laundry baskets. So there were all kinds of interesting scheduling problems where we had to think about not only what sorts of products to make, when, how many of those products to make, but also a color sequencing aspect of it. And that was really a pretty interesting problem that clearly involved a lot of OR types of modeling as well as solution approaches to solve.
During my master's, which my thesis was stochastic terrain profile modeling, and I'm trying to use that and relate it to operations research. It also had to deal, I guess if you would extend the research, it also had to deal with fuel efficiencies, more of a vehicle dynamics aspects. So it relates, I think it relates to ORs in several aspects of that nature. The concept of that is to create the topology of the terrain. I'm also incorporating stochastic soil models. But I guess taking a step back, I think that's very detailed. Taking a step back and understanding what that is, it's more for vehicle dynamics, understanding, let's say for example, for the Army, you want to send a tank over to Iraq. You have to create your vehicle, create your suspension so it could fit your terrain models.